Good morning, everyone. From this point, I'd like to thank the Scientific and Organization Committee of MedFrat 1. I think it's a very important scientific event, and I'm really glad to be here. Today, we will be talking about the luminescence efficiency of single crystals, and more specifically calcium fluoride doped with europium. And we will be talking about the temperature dependence of such crystals. This is especially important because lately in very specific research there is need to measure some parameters using detectors. So these kind of crystals are being used as the detectors, like X-rays, like gamma rays, in a very harsh environment. For example, when we try to extract oil from the earth, or when spaceships try to approach the sun, and we have very high temperatures. At the University of West Attica, where I belong, we also do research in medicine and medical technology at the biomedical engineering department, and this is also very important because we try to use this kind of detectors in medical systems, medical imaging systems mainly, like computed tomography, CTs, or MRIs, or other modalities for imaging. In this way, we want to use this kind of crystals to try to measure photons and try to make an image out of the human body with this kind of crystals incorporated. To continue, the aim of this research was, as I said before, to try and see how this specific single crystal reacts when the temperature rises. For example, how much light it gives. It has to be tested in extreme temperatures, because this kind of temperatures are being used, as I said before, in spaceships and in other conditions like oil extraction. So at the moment there are companies like Saint-Gobain that already produce scintillators for these harsh environments, and this kind of scintillators that are currently available in the market are this kind of scintillators, but not the one that we study. So how do we study that? How we make the research? We take the crystal, we increase the temperature pretty high, and then we measure the light that is produced when this crystal is irradiated by X-rays or any other radiation, but at this project we used X-rays. So we measure how much light comes out of it. So we measure the light at room temperature, and then we increase the temperature and see how the absolute efficiency, which is actually the amount of light that is coming out of the crystal, is changing. Okay, why? This is a small table showing some of the parameters that are related to calcium fluoride doped with europium. The main reason there's a lot of reasons why we chose calcium fluoride doped with europium to study. One of the major reasons was the fact that the melting point of this crystal is 1418 degrees of Celsius, meaning that we can use this crystal at these very high temperatures without destroying the crystal. Another reason is that it's pretty robust to mechanical and thermal shocks, which is also very important, because if we find out that this crystal is really useful for us, then we have to apply some mechanical force to give it the right shape and everything. The crystals we used in our research was bought by Advatec, UK Limited, and the crystals had dimensions of 5 to 5 to 10 millimeters and 10 to 10 millimeters also. So the materials, as I said before, there are a lot of reasons why I chose that. Except the high melting points, the robustness and the thermal and mechanical shock is also important, as well as hygroscopicity. This kind of crystal its hygroscopicity tells us that it can easily be used in contact with solutions, direct contact with solvents and aqueous environments, which is very important, especially in marine research. The other reason is that it's quite easily machined, which, as I said before, it's pretty important because we have to have it first of all in very specific sizes. Size is quite important. Like, for example, when we have a drill to the earth, the available space for these kinds of sensors is very limited. So we have to find a way, and you have to find the materials to give the right size and shape without destroying. This kind of material is pretty easily machined, and it can be used in lots of applications. The energy resolution of this crystal does not change with the temperature increase. This is something that has been studied by other research teams and has been already published. So this is also very important, because if we find a nice crystal that gives out a lot of, it has a good absolute efficiency, but it has low energy resolutions in high temperature, then it's not good. Doesn't fit our applications. So this is a good example of good energy resolution at high temperatures. The low self-absorption it exhibits is also very important. One of the main problems that more crystals have is that they produce light that they self-absorb. So they produce the light, but they absorb the light they produce. So the final outcome, in many cases, is not good. It's not good enough for our applications. In this case, the crystal does not really have high self-absorption, which means that we can use the light that's being produced. And last but not least, and I would say it's quite important too, is that this kind of crystal is easily found in nature. That makes it low-cost material to have. So you can have these crystals in very low prices, and we can easily use it for research or in every application without increasing our cost. So this is actually part of the experimental setup we used. I would be quite brief. This is an X-ray lamp. It produces X-rays. We used an X-ray machine that is currently used for X-ray imaging. We used an aluminum filter of 20 millimeters just to simulate the absorbance of X-rays of the human body, since our applications could be used in medical imaging. we would like to use X-rays like in real life. For example, when we have a patient standing between the crystal and the X-ray source, the X-ray spectrum is changed. There are changes because of the photons that are being absorbed by the human body. So we simulate this absorption by this aluminum filter. Then we have the integrating sphere with the photomultiplier. This long instrument here is the photomultiplier, and this is the integration sphere. What we do with this is that we collect all the light that is being produced by the crystal. We collect it 360 degrees around. So with this, with the integrating sphere. Then we have attached the photomultiplier, so we can have this as an electrical signal to process. The rest of it is actually an electrometer and an analog to digital converter, just to digitize the signal and feed it to a PC in order to measure it and have it plotted. To sum up, we have X-rays coming out of the source, go through the aluminum filter which simulates the human body. They hit the crystal which is on top of the integrating sphere. The integrating sphere collects all the light that is coming out of the crystal, 360 degrees, and the output of the integrating sphere goes as an input to the photomultiplier. The photomultiplier makes the light an electrical signal which is traveling along through this instrumentation, and through an analog to digital converter we make it in a digital form to process it. That would be all for... Well, we used X-ray energies from 50 to 130 kVps. This is the range of X-rays that are being used currently in medical imaging. And this was a Merate BMI lab. So this is how we did the measurements, but how did we increase the temperature of the crystal? The only thing that has been changed in this schematic is that we used the heating gun, a heating gun, to increase this. This is the crystal, and this is the integrating sphere, and this is the photomultiplier. So we increased the temperature of the crystal with the heating gun up to 123 degrees of Celsius. And we used this infrared laser thermometer with accuracy 0.1 degrees of Celsius to measure the temperature at all instances, the temperature of the crystal at all instances. So we have been starting to make measurements at temperature, at environment temperature, like 22 degrees. And we started increasing the temperature. We were measuring at the same time the temperature with the infrared laser thermometer, and we were doing all the measurements as described before. This instrument, the Piranha instrument, I'll go one step earlier. In order to measure the absolute efficiency of the crystal, we need to know very precisely the amount of X-ray photons that hit the crystal. So we used this machine to measure the X-ray flux. These are the results we had. Actually, this is the dose that was coming out of the X-rays. And this is the actual results of the temperature. What we found out? We found out that the maximum absolute efficiency, this is translated like the maximum light that is coming out of the crystal compared to the X-ray photons that were hit the crystal, was maximum at the lower temperature, which was the 22 degrees of Celsius, and it was decreasing while we were increasing the temperature. The lowest was around 128. Why the temperature is decreasing? Sorry, why the absolute efficiency? Why is the light decreasing when we increase the temperature? This is actually happening just because we have non-radiation relaxation mechanisms that are increasing when we increase the temperature. This is why we have lattice vibrations that do not produce light, they do not produce radiation, that are increasing when we increase the temperature. That's the main reason. Just to make it quick, these are the conclusions. It's actually a sum up of what we have already said. Thank you for your attention, and I will be happy to answer any questions you may have.